All right. Second method of finding volume is something called the show method. If you only know the disk method, you're not going to be able to find the volumes of everything that we want to find right there. So here's our new steps to find the volume using the show method. We have a different formula you want to get down these steps here. Now, let me just, in this video, I'm just going to talk about the understanding where this formula comes from a little bit. And then I'm going to actually show you why we need the show method. And in the next video, I'll have the nuts and bolts part of the problem where I'll work out several examples and talk about how I know when to use the disk method or the show method there. Sometimes a picture gives it away, sometimes the equation gives it away. But if you only know the disk method, we just came from that assignment where you're just always drawing the disk method, you're making your rectangle perpendicular to your axis of revolution. So if I have this equation and this curve, and I'm gonna revolve this thing about the y-axis, there's my axis of revolution there. If I only know the disk method, I can't do this particular problem right here, because if I do the disk method right here, I would draw my rectangle perpendicular to that x-axis. I'm sorry, to the y-axis, to my axis of revolution, my y-axis. And then notice right here, this little part is vertical, which would make that a dy problem. Now, two issues with this. One, when I drew the rectangle, it went from a curve to the same curve. You never want to do that. That seemed a little bit odd. That last homework assignment you just did, you never did that. We always went from a curve to a straight edge or a curve to a different curve there. So you never want to draw your rectangle where you're going from a curve to the same curve. That's not going to be useful for us. Also, the other issue with this is the equation. Look at this equation. If you say this is a dy problem, like if I give you y equals x squared, I can easily make that x equals the square root of y. And so I can use the x version of that equation. I can make that a dx problem, or I could use a y version of that equation, and that could be in terms of y, and I can do a dy problem. But this equation right here is y in terms of x's. I can't solve this like this and get x equals something in terms of y. Like you can't do it. You could do a GCF, but you still can't have x equals something where you have nothing but y's over there. It can't be done, okay? So the picture kind of dictates on this one that I don't want that scenario, and the equation dictates that this can't be a dy problem, and if it's a disk method, it's perpendicular, that's a dy problem right there. And so what would fix that? Well, it would fix all of these problems if I had a technique where I can go parallel to the axis of revolution. So forget this rectangle. If I was able to draw a rectangle parallel to that axis of revolution, knowing you're going from a curve to a straight edge, you're not going to go from a curve to the same curve there. So that fixes the picture. And then also, if you draw your rectangle parallel to that axis of revolution, that y-axis, this little part is now horizontal, creating that to be a dx problem. And this is what we need. The equation dictates that if that's y in terms of x's, this has to be a dx problem, because I can't solve and get it in terms of y to create a dy problem right there. So if I have a technique that's parallel to the axis of revolution, then I have all my bases covered, where I can do a dx problem or a dy problem, depending on the equation, depending on the picture right there. So that's the reason why we need a different technique other than just that disk method. So that's what the show method is going to do for us. We're still going to draw the bounded area. So draw that, use your graphing calculator, I don't care, but get that bounded area down on your homework paper there. We got to see that picture, and then label your axis of revolution there, put a couple numbers on there. And this time when we do the show method, we're going to draw a rectangle parallel to that axis of revolution. And then this third step is the same as your disk method notes. Your dx or dy, I told you I would keep that consistent for you. Your dx or dy is still determined by the width of your rectangle. So if you draw it up and down that little part, remember the width is a little part, that's horizontal like the x-axis is, so that's a dx problem. If you draw sideways, that little part is vertical like the y-axis is, that's going to be a dy problem. So that's the same as a disk method. So far of these first three steps, the only difference is we're going to go parallel versus perpendicular from the show method, from the disk method to the show method right there, right? So we're going to do the same thing that we did in the disk method, except we're going to go parallel to the axis of revolution. And instead of a capital R and a little r, we got this P and the H in there, okay? And so let me just kind of talk about now where this formula kind of comes from right there. When we say shells, we're not meaning like pasta shells. What we're meaning is cylindrical shells. This is pretty neat. I had a former student actually 3D print this thing for me, okay? When we say shells, we're talking cylindrical shells. So if I want to find the volume of a particular shape, what we got here are all these cylinders. Sometimes, you know, we're going to have holes and things in there, but we got all these cylinders, and it's like an outer shell, like a snake skin. When a snake sheds its skin, and then you just rip off a little part, rip off a little part there, and just like a shedding its skin there. If we took a bunch of those like things that it shed off, we could find the volume of that thing. So we've got outer shell here, outer shell here, outer shell here. We're just going to pick up these outer shells. And what we're going to do is find the volume of each one of these outer shells. Just like when you look at Tootsie Roll Pop there, each lick, you're taking out a little bit of that area, a little bit of that sucker, a little bit of that sucker. And then if you add up all those licks, you know, and I don't know, it's a little bit of a weird example there, but if you add up all those licks, that's the volume of that Tootsie Roll Pop, right? So this thing is pretty neat there. It's just kind of like, hey, this is 3D printed. It's pretty darn nifty right there. But that's what we're going to do. And then I got like a few other manipulatives here to kind of show you where this is coming from. Now, if you take, the reason you got this 2 pi times this pH right there, P is the distance from your axis of revolution to your rectangle. And when you're going to see me when I work out the problems, I'm going to use the same thinking as when we did the capital R and the little r. We had those 4 big scenarios that we talked about. I'm going to use the same thinking right there. That P is different from the capital R and little r, but it's the same thinking because you're measuring the distance from here over or there back. It's still going to be that same thinking as you're measuring distances. So capital R, little r, and P, you use that same distance with our 4 big scenarios. And then the different one is the height of the rectangle. The height of the rectangle, when the rectangle is like this, I'm always going to go top y minus bottom y. When the rectangle is like this, it's always going to be right x minus the left x. Because if you think about it, if you did like, hey, if I said what the height of this rectangle is, if this is like 2 and this is 5, we know the height of that rectangle is 3, right? But what we really did is a top y minus a bottom y. And then over here, if I have this is 4 and this is 7, and I said, what's the height of that rectangle? The height of that rectangle is also 3, but I did a right x value minus a left x value. So if we always think of it like this, but see, we're really going to need that if I give you a couple different curves, like a curve here and a curve here, and remember as my rectangle, that top y is changing. So we're going to need to use the equation like y equals x squared or something like that, right? And then right here, the bottom y would be right there. So we'll talk about that in the next video, and I'll extend that a little bit more. But let me just talk about where this formula comes from. I should just say that for the next video, but we're okay. Let me talk about where this formula comes from. If you take like a cylinder, if you take like a Campbell's soup label, right? If you unravel this label, right? I think we all know, or if you want to find volume of that, or if you take like a Kleenex box and you rip out a Kleenex, and then if you had that soup label, I guess I could have ripped out the soup label there, but if you just unravel the soup label and think about what shape that creates, you get a rectangle, all right? Like a Kleenex, okay? And then the thing is that rectangle, it started off as a circle, right? And then you unraveled it. And so if I said, what was this thing right here? That would be the circumference of that circle. See, it started off as circular and then you unraveled it. So the circumference and distance around that circle will give us that length right there. And then you'll times it by the height. And so the circumference of a circle is 2 pi r, right? Now we're not going to use the r's because that's going to confuse it with the capital R and little r, that this method. But that's the reason why we have this 2 pi P in there, because that 2 pi P, that's like when I unravel that soup label, that's the length of that segment right there, right? And then when you times it by the height, that gives me the area of that Campbell's soup label, or that area of that Kleenex right there. Or, you know, sometimes I bust this out for this section there. So I'm teaching this stuff in class, because like, if you just smell these right now, I just smell so lemony fresh, man. I just like to smell those things there. It makes it, you get that nice clean smell. But there's where the 2 pi P times H. So the 2 pi P is when you unravel that. And then when you times it by the H, you're going to get that. And so what that's going to give us is like the area of this whole outer part right there. And then, but the thing is, we're supposed to find volumes, right? And so that's where the dx or the dy comes into play. If you take a Kleenex, the Kleenex has a little width to it, right? So that little width right there, that's like the dx or the dy part, creating that 3-dimensional shape. And so you got this like Campbell's soup can, you can unravel it and whatever, but see the dx dy, this cylindrical shell, this shape that I just showed you, all these cylinder pieces, they have that width to them. That's the dx part, that's the dx or the dy. So that's the part that turns it into the volume and then that 3-dimensional shape for us. And we know the integral is an accumulator, and it's going to add up all those pieces for us. So we'll add up like the volume of this piece and the volume of this piece and the volume of this piece, put a bunch of like infinite amount of those in there, and then it'll be like the sandpaper to kind of smooth out those edges, and it'll give us the volume of the 3D shape that we want right there. So that's the understanding part with the shell method. And then please watch the next video. Next video, I'm going to definitely talk about how I know to use the shell method versus the disc method. All right. Don't assume that the shell method doesn't always work. The disc method doesn't always work. It depends on the picture. It depends on the equation. So I'll talk about when to use which one. That'll be an important video. And I'll work out some examples using the shell method.